any location in the sky using a unique set of coordinates. To do that, let's first use an analogy. We know from Earth that we can take our own rotation axis and use that to divide the Earth along the equator into northern and southern hemispheres. But that also means that we can now draw parallel lines to the equator, giving us what we call parallels of latitude. So we start at 0 degrees at the equator, and we arrive at 90 degrees north at the North Pole and 90 degrees south at the South Pole. Now, in addition to parallels of latitude, measuring north and south, we also want to be able to measure from east to west. So by international agreement, the prime meridian is an imaginary line that goes through the North Pole, through Greenwich, England, at the Royal Observatory, all the way down to the South Pole. And then we can simply measure east or west in terms of meridians of longitude. So, for example, here in Baltimore, we are at 39 degrees north latitude, 76 degrees west latitude. A southern example would be Cerro Paranal in Chile, that's 24 degrees south latitude or 70 degrees west. And Rome, Italy is 42 degrees north and 12 degrees east. So that places Rome at about the same latitude as Boston, Massachusetts. Now, that is how we define every location on Earth. And we're going to use an analogous system to define every location in the heavens. So let's bring our Earth inside of the celestial sphere, and we'll once again extend our north and south poles to form the north and south celestial poles. We'll extend the equator to form the celestial equator. And just as we did before with parallels of latitude, we can now draw parallel lines to the celestial equator, only we refer to these as parallels of declination. So we measure declination as 0 degrees from the equator, all the way up to positive 90 at the north celestial pole, and then all the way down to negative 90 at the south celestial pole. Now, we cannot simply take our meridians and apply those to the sky as well. The reason for that is because the Earth is rotating, and therefore the meridians would need to rotate as well, and that would make such a system fairly useless to us. Instead, what we'll do is we'll take the annual path of the sun, the ecliptic, and we'll note the location that the sun is on in March when it arrives at the vernal equinox. Since the Earth rotates on its axis once every 24 hours, this gives us a 24-hour clock face that we can write onto the celestial equator. So when we draw parallel lines to this clock face, we then get hours of right ascension. So again, think of not so much as hours of time, but think of it instead as hours on a clock face. For example, Rigel in the constellation of Orion has a right ascension of a little more than 5 hours, about a quarter of the way onto the 6th hour circle. So that gives Rigel a right ascension of 5 hours and 15 minutes. And since it's south of the celestial equator, that gives us a declination of minus 8 degrees and 12 minutes of arc. Remember, we can take a single degree and we can split that up into 60 minutes of arc. So this coordinate system, since it's based on the celestial equator, we call this the equatorial.